Welcome back to this module on dynamic exploitation of ILP. The topic of this lesson is hardware-based speculation. First, a bit of motivation. In the dynamic execution example presented a few lessons ago, we assumed perfect branch prediction, meaning instructions are fetched and issued as early as possible, but not actually executed until the branch is completed. Because of this, every iteration we lose a cycle, as highlighted in red in this scheduling table. Although the load from the second iteration has been issued in clock cycle 6, it cannot execute until clock cycle 8 because it has to wait for the branch to complete. In this case, the penalty is small, but if the branch delay is 10 or 15 cycles, as is common in modern deeply pipelined processes, the pipeline will be very large. Speculation, which is the topic of this lesson, aims at overcoming control dependencies. It does so by first predicting the outcome of each branch, and second by speculatively executing the predicted instructions as if our guesses were correct. Speculation can be performed in hardware or in software. In a later lesson I will describe several mechanisms that support speculation by the compiler. The focus of this lesson is hardware-based speculation. The key idea behind speculation is the following. We allow instructions to execute out of order and speculatively, but force them to commit or complete in order. Furthermore, the instructions are prevented from doing anything that cannot be undone until it commits. The hardware structure needed to support speculative execution is called the reorder buffer. Instructions wait in this buffer until they are no longer speculative. In other words, they wait in the reorder buffer until it is known that they should have been executed. After that, the instruction commits. Sometimes the commit phase is also called complete or graduate, but let this not confuse you. Speculative instructions are not allowed to change the state of the processor. For example, a speculative instruction is not allowed to write a register or to write to memory, as long as it is speculative. As we will see later, the ROB is also used to provide precise exceptions by taking exceptions only when the accepting instruction commits. The reorder buffer is like a ticket dispenser where every instruction pulls a ticket telling when it is its turn to commit. Tickets are pulled when instructions are issued and they issue in order. After an instruction has taken a ticket, it can go off and execute, provided of course its operands are available. But the order of commit is determined by the number on the ticket. Now I describe the basic structure of the reorder buffer. Conceptually, the ROB is a first in, first out queue with entries consisting of 4 fields. The first field denotes the type of the instructions contained in the entry, such as an arithmetic instruction, a load, a store, or a branch. The second field indicates the destination of the instruction, where it writes to. For a load and an arithmetic instruction, it indicates the destination register, and for a store, it denotes the memory address where the data should be stored. The third field is a ready flag that indicates if the instruction has completed execution or not. The fourth and final field of each entry is the value field. It contains the result of the instruction. In other words, the value computed by the instruction. This figure illustrates a reorder buffer with 4 entries. The bottom 3 entries are occupied and the top entry is free. We must also maintain a head and a tail pointer. The head pointer points to the oldest instruction in the ROB. This instruction should commit first. The tail pointer points to the youngest, most recent instruction in the ROB. New instructions are inserted into the ROB after the tail pointer. So the program order of the instructions in the ROB is from bottom to top. This figure shows the organization of a floating point unit based on Tomasulo's algorithm extended with speculation. The reorder buffer is highlighted in red at the top right. I will now explain the differences between this figure and the figure we have seen in a previous lesson that implemented Tomasulo's algorithm without speculation. First, the register file is written from the reorder buffer instead of from the common data bus. This is to ensure that speculative instructions do not write the register file. Second, the ROB can also supply the operand values in addition to the register file and the common data bus. If the operand values are both in the register file as well as the reorder buffer, we must use the values in the reorder buffer since these are the most recent values. Third, the store buffer has been eliminated from this figure. Its function is now integrated into the ROB. Fourth, there is a connection from the address unit to the ROB. This is because the address unit computes the effective address of a store, and this must be stored in the destination field of the corresponding ROB entry. Fifth and finally, results must be broadcast on the common data bus together with the number of the ROB entry that contains the instruction that has produced this result. This is needed to know where the instruction needs to be stored in the ROB. So every in-flight instruction must carry its ROB entry number. When we support speculation, every instruction involves 4 phases. The first 3 phases we have seen before, but what happens in them might have to be extended. The 4th phase is new. In the issue phase, the next instruction is retrieved from the instruction queue and issued to an empty reservation station. In the execute phase, the instruction is executed, provided of course its operands are available. This execute phase is identical to the execute phase of the original Tomasulo algorithm, and I will therefore not discuss it anymore. In the write result phase, the result is written onto the common data bus and from there into the ROB, as well as to any reservation station waiting for this result. Finally, there is an extra phase called commit. In it, the instruction at the head of the reorder buffer commits. I will now describe each phase except the execute phase in more detail. First, the issue phase. We issue the next instruction from the instruction queue to a reservation station and a reorder buffer entry. If there is an empty reservation station and an empty reorder buffer entry. The instruction is issued together with operands from the register file or from the value field of a reorder buffer entry. It is possible that several instructions in the reorder buffer write the same register. In that case, the value field from the youngest ready ROB entry should be taken, since that one contains the most recent value. It is of course also possible that the producer instruction of the operand is currently in flight in a reservation station. In that case, the instruction should be issued together with the identifier of that reservation station. The second phase that needs to be modified when we support speculation is the write result phase. The result is written onto the CDB not only to all awaiting reservation stations, but also to the reorder buffer. For that reason, instructions need to be tagged with the number of the reorder buffer entry that contains that instruction. Special actions are required for store instructions. If the value to be stored is available, it is written into the value field of the ROB entry for that store. If the store value is not available yet, the reorder buffer must monitor the CDB until it is broadcast, at which time the value field is updated. Finally, the commit phase. In this phase, the instruction at the head of the reorder buffer commits if its ready flag indicates that the instruction has completed. When an instruction reaches the head of the reorder buffer, we know that it should have been executed and therefore it is safe to change the state of the processor. For different types of instructions, different actions have to be taken. Arithmetic instructions and loads write to the register file. Stores, on the other hand, write to memory. A correctly predicted branch finishes. This simply means that the head pointer is updated so that it points to the next instruction. When an incorrectly predicted branch reaches the head of the reorder buffer, however, it indicates that the speculation was wrong. In that case, we need to flush the ROB by setting the tail of the ROB to the entry holding the branch, which must be the head of the ROB. Furthermore, we need to restart execution at the correct successor instruction of the branch. Here's an example. In this example, the branch at the head of the ROB is ready to commit, and the load and the arithmetic instruction have been executed speculatively, and the arithmetic instruction has completed, but the load not yet. If the branch has been incorrectly predicted, the tail will be set to the head as shown here. This flushes the load and the arithmetic instruction that have been wrongly speculated. Execution is now restarted with the correct successor instruction of the branch. An additional advantage of the reorder buffer, besides supporting speculative execution, is that the reorder buffer can preserve the exception behavior of the program. Recall that preserving exception behavior means only exceptions that would occur when instructions are executed in sequential program order should occur. This implies that speculative instructions may not generate exceptions since it is unknown if they should be executed. In order to dynamically execute while preserving the exception behavior, we need to separate the raising of an exception from taking the exception. That means that if an instruction causes an exception when it is executed, the exception should be raised in the reorder buffer entry that contains the instruction. Thereafter, when the instruction reaches the head of the reorder buffer and is ready to commit, we take the exception if it has been raised. Here's an example. In this example, the divide instruction has raised the division by 0 exception as indicated in the ROB. The divide is still speculative, however, since the branch at the head of the ROB has not committed yet. If the branch commits and has been correctly predicted, the head pointer will point to the divide instruction. Now the divide commits and the exception is taken. If the branch would have been incorrectly predicted, the divide would have been flushed before it reached the head of the ROB and the exception would not have been taken. Because instructions commit in order and only when they are no longer speculative, this ensures that only exceptions that should occur do occur. I end this lesson with some advantages and disadvantages of speculation. Speculation is a kind of gambling, and we all know that gambling is risky. The advantages of speculations are that it allows using functional units that would otherwise be unused for several cycles and that it eliminates control hazard stalls. Speculation also has a number of disadvantages, however. First, it consumes time and energy, which is wasted when the speculation was wrong. Second, it requires additional hardware and power. Third, if we are not careful, speculation may even reduce performance when the speculative instruction causes an exceptional long latency event, such as a cache miss or a TLB miss. If we speculatively execute a load and that load causes a cache miss, then handling the miss will take time, and this time is wasted if the speculation was wrong. This brings me to the question, how much to speculate? Should we continue the execution of a speculative instruction when it causes an exceptional event or not? The typical solution to this dilemma is to speculate only on low-cost exceptional events, such as level 1 cache misses. If a speculative load causes an L1 cache miss, then the miss is handled by loading the data from the L2 cache. If, however, the speculative instruction causes an expensive exceptional event, such as an L2 cache miss, a TLB miss, or even worse, a page fault, then the processor waits until the instruction is no longer speculative before it handles the event. For example, we will not handle a page fault, which means loading a page from disk, which takes millions of cycles, when we are not 100% sure that the instruction should have been executed. This completes this lesson. Thanks for watching. In the next lesson, I will discuss multiple issue processors, whose goal is to issue and execute multiple instructions in each cycle. In addition, I will provide an example that shows how the individual mechanism of dynamic scheduling, speculation, and multiple issue work together. Hope to see you back.